Thank you, Ian. What Ian didn't tell you is I was lucky enough to be invited to speak back at the second Codemania as well. And the reason for that was Ian was trying to rotate the speakers so that he didn't have kind of the same people year after year. But I'd expressed an interest, and Ian, unfortunately at the time, was drunk and said, "We'd love to have you back. We'd love it. We love it. We love it." And he sobered up and thought, "Oh my goodness, what have I done?" And he told me this often, "Ian, it's okay. You can tell me that." But too late. By then I'd accepted and it was all good. The other people I'd like to thank are, of course, Microsoft Marketing. I've been working for startups for a little while and been doing my own thing, but now I actually have Microsoft Marketing to help me with my talk content. And they have asked for a few small changes. We had a conversation about what a zygohistomorphic prefromorphism is and said, "Is it a Microsoft product?" And I said, "Well, no, not quite." So they said, maybe you could change it. Maybe you could have something that's a little bit more concrete for people to latch onto. So I've added a bit of that, and they said, well, you also need to give them some business context so they know whether it's for them or not. Well, okay. And we appreciate that you're helping to build a brand around SharePoint by loving it, but perhaps something a bit more practical for people? Well, okay. And stop worrying. Do you know they said, do you know what makes developers stop worrying? It's stuff that Peter and Catherine were talking about. Automation. Automation makes developers stop worrying. And we have just the tool for you, they said. And no one cares how you learned, Ivan. They want a call to action. And that, ladies and gentlemen, is how MSDN articles get their titles. On the plus side, I can promise you that by the end of this talk, you will know as much about deploying SharePoint as I do. So Gary Bernhardt's talk this morning was very interesting to me. He was talking about he started out by talking about three very different things: the React framework, the bundler tool, and Git source control. And he teased out commonalities between them in that each one sort of built an architecture of pure functions producing result sets, which then some impure component then took and munged with the horrible, scary world of the DOM or installed gems or whatever. And that echoed with me because the concept that Gary teased out from that was pure function. And what I want to talk about here is, again, that process of teasing out powerful commonalities, powerful abstractions between apparently disparate things. I'd like to begin by stepping back to the dawn of history. This is an early IT shop. You can see the guy on the right coding up the Millennium bug there. And you can also see up at the top, there's a manager. You can tell he's a manager because he's not down in the office with the wild pigs. And he's saying, "Perkins, what's good for business is good for America. Double all the prices." This is actually how Microsoft Marketing works as well, by the way. And I can't write early assembly code or Fortran, so I had to translate it into BASIC, but I hope people recognize that. So the structure here is, for such a small function, it's pretty self-explanatory, but notice that in line 50, towards the end of line 50. Now, some of you will not recognize that penultimate word on line 50 because you're young and you didn't suffer through this. But that's how we used to do all programming. We didn't have we kind of had for loops, but that was about it. But if you wanted to chain things together, you used this goto thing. And it was chaos. It was just chaos. Everything was sort of hardwired to everything else, and it's very hard to tease things apart. And then this guy came along, and he wrote a little letter to the communications of the ACM saying, "Gosh, this is an awful pickle. I don't think this is necessarily the most brilliant idea in the whole world." And the editor of the ACM thought, "That's not very snappy. I'll call it go-to statement considered harmful." And the world caught fire. This is Edgar Dijkstra. I can pronounce archaisomorphic free polymorphism, but I can't pronounce his name. He was one of the big proponents of structured programming, which was sort of the big revolution that happened in, I guess, sort of the late 60s, early 70s, going from those very go-to-driven, jump around, everything is coupled to everything else, global variables everywhere kind of designs, to having things more localized and contained within modules, using structured constructs to put things together. This is an early for loop from the C language. Modern for loops are a little bit nicer. And you can begin to see we've taken away some of that abstraction of seeing how the microprocessor, the CPU, kind of jumps around from place to place and manages memory and all of that sort of stuff, to a higher level of abstraction where we're manipulating lists and we're having loops that the compiler takes care of for us. Fast forward to the present day. I didn't know what I could show for the present day show. This is a picture from a Microsoft tour video of an Azure data center. And off topic, I kind of like it because it not only shows kind of the street view kind of design and where the package, but it also shows we have operational excellence, apparently localized into that black box at the top right of the picture, which is not true. Operational excellence is actually a guy called Pablo in Building 42. But one of the strands that went on in parallel with the sort of the classical imperative programming paradigm was development of a sort of more declarative paradigm. This is a Lisp-ish kind of thing. Lisp dates from 1958, and this is doing again the same thing of doubling all the prices, but you can see it's doing it a different way. There's no explicit looping, there's no jumping, there's no movement around. There's almost no variables in a way. There's the prices thing, but that's source. And there's the function, this lambda thing. It's probably going to be a little bit more familiar if I show you the C# version of it. C# calls it select instead of map car. Other languages might call it map instead. But again, you've got that increasing level of abstraction. You're no longer worrying about how do I traverse this collection? How do I actually navigate my way around? You're going, I've got a collection, I want to do an operation on it. I've got all the prices and I want to double them. And that's what that says. Very precisely. So we're able to start pulling out from these implementation details of loops or go-tos or whatever, these higher level abstractions of select or map, where or filter, sum, product, maximum. But there are some things where that doesn't sort of work out, and if we haven't got sort of pre-canned operators, do we need to fall back on this loop construct? Well, if you looked at those previous ones, you'll see there's a lot of commonality between them. And we can kind of pull that out into this pattern. So we're doing a for each over the collection. We've got an accumulator or a result, and each element of the collection is resulting in an update to that result based on a sort of single step function. So we're folding in kind of one X at a time into the result, and when we're finished, the result comes out. We're accumulating things. And C# calls this aggregate, and it's one of the link operators. And other languages, again, will have something similar. May not call it aggregate, but whatever. So now we have another abstraction, the aggregate abstraction, and it turns out that we can implement sum in terms of that abstraction. We can implement product in terms of that. We can implement max in terms of that. And we can implement our Babel feature in terms of that. So anything that is kind of condensing a list down to a scalar, to a single value, we can now do in terms of that one thing. It's a very, very powerful component. Very, very powerful abstraction. And although C# aggregate calls it aggregate, for the visual reasons I've told you, functional programmers call it fold. That's the language that's been adopted by the FP community. So you now know the secret. You've now been inducted into the mysterious world of functional programming without even knowing about it. Turn to the person next to you, give them a high five and say, I'm a functional programmer too. Well done. So fold takes an accumulator function, a starting value, which I've kind of elided from my samples, and a sequence, and it produces a value. One of the nice things about the name fold is it suggests a symmetrical unfold operation. And if fold collapses a list down into a value by having a function that joins two values into one repeatedly, then unfold should start with a single value, and it should have a function that splits that value into two and keeps repeatedly doing that. And one of those sequences is your result. So in fact, you can kind of ignore the splitting it into two. That's kind of implementation detail. But basically, you have a generator function that starts from a seed and produces new values until, for whatever reason, it runs out. And the generator function is kind of symmetrical with the accumulator function, which is why I started talking about the two things, the two results, which I shouldn't have done. So forget that. So we've got these two quite low-level operators, it seems, one of which we've deduced from a common pattern, the other one of which we've kind of worked out by going, well, what if we just sort of turn things around? What if we reverse the arrows here? But I want to pursue fold a bit further. We've talked about fold as being something which collapses multiple values into one. But there's nothing in the signature of fold, there's nothing in the signature of that accumulator function that says the output, the result, has got to be a scalar. You could fold a list into another list. The result could be a list type. For example, if we wanted to implement select, we could, with a certain amount of ignoring the real functional programmers in the audience who will go, that's not how you build lists. We could go, the way that select works is we start with an empty list, and then for each value, each x in our source list, we take the old result and we stick f of x onto the end of it, and that's our new result. Go on to the next one, and we stick f of x on the end of that, and on the end of that, and now suddenly we've mapped across the list. So we can rewrite select, we can rewrite that loop, that mapping loop, in an idiom which makes it collapse into a simple fold, the fold shown on the bottom. Similarly, with where, the filtering operation, the accumulator is a little bit more complicated here because we have to decide the new result, is that going to be the same as the old result because x didn't pass the filter, or is it the old result with x stuck on the end because x did pass the filter? But it's still a fold. It's still representable in terms of aggregate. So we discovered fold by analyzing functions that collapse the list down to a scalar. We looked at sum, product, and max, and suddenly it seems we found something that we can actually use to implement a very, very wide range of operators. We found an extremely powerful abstraction, extremely powerful component that we can use to do things that we never originally intended it for. I want to put that on hold and step away from the world of data structures for the moment. Sorry, away from the world of mapping operations. And I want to talk about data structures. So we've been talking about sequences initially. We talked about mapping sequences, for example. And this is our familiar C# select or map or mapcar or whatever operation. We've got a sequence on the left-hand side. We perform a map operation that maps each element, and we end up with a sequence on the right-hand side. This is all pretty familiar. But it's also pretty clear that's not the only thing that you can do this mapping operation to. For example, if I've got a tree of some type, then I can perform a mapping, I can apply a function to each element of that tree while keeping the shape of the tree. So here I'm going to apply the function to the top node, and that turns out to be the top node on the right. Then I'll do it to the one on the left and put that in on the leftmost node there, then that intermediate one, and so on. So we're keeping the shape as we transform. How many people here are familiar with the idea of option values? Options or maybes? Okay. How many people here are familiar with the concept of nullable, like C# nullable? Okay, a few more. So the idea with option is this kind of a generalization of nullable, which is to say it represents a thing that may or may not have a value. So for example, if you were to query a database for a customer by ID, there might or might not be a customer at ID. So it would be appropriate for that query function to return a maybe of customer. Either we get a customer, in which case we've got an object, a value, or we don't get a customer back, in which case we've got nothing. It turns out that map makes sense for options as well. And the way that it will be defined is if there's a value, if the maybe has got a value, the option has got a value, we apply the function to it. And if it hasn't, then we continue to return the hasn't got a value case. So we're ending up with a maybe, we're starting with a maybe of triangle, we're having a map of triangle to oval, and we end up with a maybe of oval. Does that make sense to people, that we can apply maps to options? So we can see some commonalities between those three cases, although they seem kind of unrelated. There's something that works in the same way. All of them have got this idea that we can take a thing and a function and get to another thing, potentially of a different type. Remember, this might be a sequence of A being mapped to a sequence of B, a sequence of string to a sequence of integers, for example, a tree of string to a tree of integers. So we have the idea of map, and that suggests there's some sort of notion that we haven't quite captured yet, that there is something, which I've called F here, which sequence, tree, and maybe all share. So when I see a thing like that, I want to give it a name. And being a good enterprise developer, I'll give it an awful name. Give it a very explicit name. Unfortunately, the mathematicians got to this idea before I did, and they called it Functor. High five to the person next to you. You are now a functional programmer. You've been initiated. Well done. And again, I just want to take a little byway into kind of explaining that. If you go and ask a mathematician what a functor is, firstly the mathematician will kind of stare blankly at you and go, "I'm not a category theorist. Go ask. There's only 3 of them in the world. Go ask them." But if you're lucky enough to find one who is a category theorist, then they will give you a different explanation of what a functor is. They will not talk about a map method or anything like that. But if you think about this signature, then we can kind of rewrite that as map is a function from sequence of t and a func of t to u to a sequence of u. And similarly with map on trees and map on maybes. But if I now think about, and I can reorganize that, I can just reverse the order of the arguments because nothing ever goes wrong when I reverse the order of the arguments. The compiler will catch that for me. Life's good. Nothing can go wrong. Now this is saying that map takes a function and a sequence or tree or maybe and produces a sequence or tree or maybe. But if I kind of imagine re-bracketing that, then sequence of t to sequence of u is exactly a function from sequence of t to sequence of u. tree of t to tree of u is exactly a function from tree of t to tree of u. So what this is actually telling me is that map takes a function on a function of objects and lifts it into the world of the functor. It lifts it into the sequence world. It lifts it into the tree world. It lifts it into the May world. It produces a new function that can be used on these functorial things, these functorial structures. All right, let's have a bit of a nose around Functor for a little while, because we found, again, an interesting abstraction, and I want to kind of probe its limits, probe what it can do for us a little bit. So we talked about the maybe or option type as being something that could return a value or not. And you might have thought, well, you know, when somebody returns, when I have a problem with my database, I kind of like to know what went wrong with it, not just have a null. So I could introduce an either type, or you might call it failable or may fail or whatever, don't know. This has got two type parameters: the type of success, which could be a customer, and the type of failure, which could be, say, a string or an exception or an integer, or how many people here remember com? It could be an H result. Yeah, you love it. Is that a functor? Well, superficially it seems not, because functor was dealing with types that had one type parameter, and this has got two. But if I think about what I want to do when I'm mapping one of these things, what I'm actually interested in a real environment, is if I've got an actual value, like customer, I want to apply my function to that. If I've got a failure, there's no actual point in trying to transform that. I mean, it's failed. We're already dead in the water. We're about to go crashing or whatever. So I'm interested in a map function. I'm interested in map being able to transform success, but not failure, which kind of looks like that. If I've got a value, I'll transform it. If I haven't, I'll just carry on returning the original error, which means that the success type parameter can vary. I can map from, say, a customer to an age, but the failure type is not going to vary. If the failure type was string, I'm stuck with a string in my failure scenario. So either is a functor, but only if I lock down the second type parameter. So either with a particular failure type is a functor, though either itself is not. Does that make sense to people? Can you see where that comes from? No, there's silence out there. That's not good. Oh, one person's put his thumbs up. Okay, we're good. If one person's got it, we're doing well. So again, remember, look back to the motivation. We want to transform successes. We want to be able to kind of chain these maps together. We want to be able to take an either, which has come back from our database query function, and apply a map age to it. So we want to transform success, which means that the success type can change. It's still that after applying the map age, we're still in the either. We may still have failed because we may have had a failure from the database, which means we cannot have transformed the value. So we still end up with an either, but it's now a either of int or string rather than either of customer or string. But it's still kind of structure preserving in the same way. And that's why it's a functor if you lock down that second type parameter. We can go beyond that. We've talked about functor as being a data structure which preserves, which allows mapping that preserves structure. But now I want to show you another type which is not a data structure, and that's the type of functions from strings to some other type. So examples of this are the length function, which is a function of string to integer. The val count, again, string to integer. The most frequent letter, which is from string to char. The first letter, which is from string to char. all of these are instances of the string2 something generic type. I'm curious as to whether the same concept that applies to maybe and sequence and tree and either applies to my string2 type. So let's try plugging in some values. Suppose I've got a function, suppose I've got a string to int over there. I've got my function, my transformer, the thing I want to map over it is square root. Well, can I compose this? Can I get something out of those which it ought to be string to double, because that's the mapping contract, is that it should produce something of the same generic type with a different type parameter. So it should go from string to int to string to double. How can I get a string to double out of length and square root? Very easily, I do the length of the string and take the square root of that. I mean, how many people have not needed to take the square root of the length of the string? Come on. And I can find other examples of this. So, for example, I can take the most frequent character and transform that and then get the ASCII value of that. So it seems like I've got a systematic way where I can put these things together, where I can take a string to some type, so string to A, func from A to B, and map will give me a string to of B. Now, given I've been going on about abstractions for the last half an hour or so, you may be going, oops, did that not go forward? Given I've been going on about abstractions for the last half an hour or so, you may be going, string? String? That's not an abstraction. So what is it about string that makes this work? What is the concept we can tease out from string that makes string to something a functor? And the answer is, there's nothing about string. Nothing at all. This works for any function type, any function type from a particular source type. So functions from X to generic type parameter is a functor. So I want you to, again, just reflect on the journey we've taken here, because it is kind of taking us into outer space a bit. We started out with the notion of being able to map over a data structure like a sequence or a tree and preserve its structure. And we identified that as sort of being equivalent to being able to lift a function from the types it's defined on, like, say, int to char, or char to int, and move that into this functorial world of sequence of char to sequence of int, or whatever. And we've kind of gone down this and found these things that we were not really expecting to be functorial actually turn out to be functorial after all. Things that we never expected, or at least I would have never expected, to have fallen into the same kind of behavior, to have anything in common with sequences or trees. As it turns out, functorial behavior is actually pretty common. In fact, it's almost hard to avoid. For example, if you define, say, a syntax tree type to represent, say, the syntax of an expression that someone's typing into a UI, then that will also fall into that category. It is so common, in fact, that the Haskell compiler now allows you to just say, oh yeah, it's a functor. Compiler, you work it out. I'm too lazy to write the code, which is my kind of compiler. So now we've got this idea under our belt of these functorial structures. Let's just come back to fold. So now I can draw a similar diagram for fold, where I've got a sequence on the left-hand side. I've got a fold function that takes an accumulator type and a single value of the sequence type and produces a new value. And the output of that is going to be a single instance, not a sequence, but a single instance of the accumulator type, the oval type. Well, I could do that on trees. I can't do it in quite the same way, but I could easily define a squish function on my trees that maybe did some sort of bottom-up. It would combine each of the leaves into something, and then it would combine those with the thing further up, and could work out the details. Maybe seems a little bit more obscure, but once again, we can define the same kind of idea of if I do a sort of folding operation where if there's a value, I'll combine my seed with the value, and if there isn't, I'll just return the original seed. That again gets me from a maybe of triangle to an actual oval. And similarly with either, where in the case of failure, I'll just throw the failure away and accept whatever default value I've given myself. So we're kind of seeing that for several of these functorial types, these functorial structures, we're able to define a way of collapsing them down, of combining them, of reducing them into a single value. And although you have to go through some colossal Haskell-y shenanigans to make it work for all functors, it turns out you can do it. These are all instances of something that is called catamorphism. And the idea of a catamorphism is you will take some sort of recursive function, you will apply it across a functorial structure, and you will get a value out of it. The details, sadly, are not as simple as I presented them there. In fact, the details I find completely baffling and over my head. But the general notion is what I want to emphasize here. This idea that we have, again, teased out a common theme from these data structures, and that it can actually be made concrete and can be used for applications. It can be used to save us writing code. You'll recall we also talked about unfolding, about being able to take a value and build it up into a list. Well, it turns out that that again has got an analog in this more general functorial world where you can build up the functorial structure from a seed from a start value. And that's called anamorphism. And it turns out there's actually quite a lot of these things. Hylomorphism is one where it first builds up a structure and then tears it down again, which you might think is a jolly worthwhile thing to do, but is actually, there are applications for it. Paramorphism collapses a structure but needs help. Zygomorphism collapses a structure, but no, paramorphism. Anyway, there's a zoo of these things. There's more than anyone would need. And at this point, you might be going, what? You told me this was going to be about sequences. This was meant to be another talk about loops. Where have we got to? Why should I care? Well, there are applications for this. I mean, it's true. If you're debugging WCF connection errors or automating or generating CRUD database websites from an Oracle schema, then you may not make a lot of use of these things immediately. But functional programming is something that is coming into the mainstream. We're not seeing a functional programming revolution, the way we maybe saw an object-oriented revolution or a structured programming revolution. But functional programming is being hybridized into existing languages with things like LINQ and Java streams and C++ lambdas, all of these things. This means that understanding the language of functional programming is going to become important. But also, we've seen that we can save code by doing this. By recognizing the fold abstraction, we can now take a bunch of code, a bunch of different disparate functions that do different things, and they can all be implemented simply in terms of that aggregate or fold operation. You don't have to worry about writing out the loops. You just go, I want to fold over this thing. So you can save yourself writing code. You can use tested code. And if you recognize other kinds of morphism, or other kinds of aggregation or unfolding, whatever, again, you may be able to reach out and find find libraries that do that stuff for you, and you just plug in your bits. If you need to write your own things, you can again separate concerns by encapsulating the business logic of this is what this particular operation needs to do. It needs to do a sum or a product or whatever, from the more abstract issue of its aggregating or its unfolding or its mapping or whatever. We only scratched the surface here. There are many, many other kinds of abstraction. And for example, in the run-up to this talk, we had a chat on an internal forum in which one of my colleagues, Mr. Mark Young over there, a very talented guy, was asking for comments on a test framework he was writing, or some test code that he was writing, where he needed to compose various bits together. And another very talented colleague, Mr. George Pollard, who is sitting right next to him now, taunting me, pointed out, oh, that's a monoid. At which point we all nodded wisely and said, yes, George. Now explain. And as a result of that conversation, Mark was able to restructure his code in a simplified way that separated concerns and was able to leverage the knowledge that we had of how monoids behave and how we could kind of build new monoids from old. So although the abstractions that I've talked about, some of them are quite remote, some are quite distant, I believe that the instinct to recognize where there are mathematical, structural underpinnings, if you don't know what all the different morphisms are, what all the different structures are, the ability to go, that looks like it should be a thing that somebody else has figured out, and I can go and ask them about it, is a very valuable skill and is going to save you effort in the glorious new functional programming world. And that is how and why I learned to stop worrying and love the zygohistomorphic prepromorphism. Thank you very much for your time.